Hi everyone, this is the continuation where I'll be going with the part 2 task. So in this I did all of them in one single collab as you can see. So let's start. The first thing I did was use a custom learning rate scheduler, and then the second thing custom dropouts, custom normalization, use TensorBoard for the visualizations, and then using custom loss function, and then use custom activation function, initializer, regularizer, and then also the kernel weight constraints. And then the next part, use custom metrics, use custom layers, use custom model, custom optimizer. And then the last thing that I did was use a custom training loop. So I'll come back to this once I'm done with the collab explanation so that we can conclude with what I did. Yeah, so this is my collab, and you can see I have the table of contents as to what I did in this collab. It is same as the one I've defined over here, but this is kind of more into detail as what I did, and then this is just a one-liner about what we did. So let's start importing everything, and then these are all the imports that we require. And then here the first one is using custom learning rate scheduler. So I defined a class called one cycle scheduler over here, and then inside that it is inherited from this, and then this is the base class that allows us to create custom learning rate schedulers that can be directly used with the optimizers. So this is the one that I have defined, and then the MNIST dataset, and then this is where I'm doing the creating my own learning rate based on that, and compiling based on that, training the model. As you can see, one cycle learning rate scheduler, and then the training and the test uh, validation loss. So so it we can see that the one cycle learning rate scheduler appears to have facilitated relatively fast training and achieved a good level of validation accuracy. So this is all about the uh, custom rate scheduler. So the next part is nothing but using a custom dropout layer. So in this I have defined the dropout layer called MC alpha dropout. So the standard dropout layer is also there, but it behaves differently during training and inference. So I have defined the MC alpha, which is nothing but it is a custom implementation that forces the dropout layer to be active even during inference, so that it is also similar to the one which we did previously called Monte Carlo dropout, so that it allows us to obtain multiple predictions for the same input by keeping the dropout active. So this is how we define the custom dropout. All of the layers are defined here. This is the class that I have, and then testing accuracy with MC alpha dropout. You can see that the accuracy was 84%, which is good. So the next thing I have done is use custom normalization. Okay, so I'm going to continue with the custom normalization where I used a custom dense layer called max norm dense. And max norm dense or its regularization is a technique that constrains the weight vectors of incoming connections to each hidden unit to have a Euclidean norm less than or equal to a specified value. So this can prevent the weight from becoming too large, which can lead to like uh, overfitting and all of that. So this is where I used define my own max norm dense normalization, and then this is the parameters that I'm sending to that. uh, a number of units, the activation, and also the max norm, and also the input shape, and then I'm testing it with uh, I'm giving that to a model. So you can see that this is where that after defining that as a layer, I'm doing the fitting of that particular model, and I'm getting the accuracy as 0.85, which is nothing but the accuracy is somewhere around 85.9%. So this is actually good. So, and then after that we have the TensorBoard integration. So like how we did it before, this is the same thing. We're defining a TensorBoard callback, and yeah, this is how we do it. This is the other way how we do it. So in the previous part I showed you one of the ways where it's deployed to one of the local host URLs, but this is the other way of doing it. As you can see, I took a model which is already there. I created it, I compiled it, and I fit it. So this is the histogram and then all of the graphs that we have over here. So yeah, these are empty now because it has been a long time since I ran. It is inactive, so I can't do anything about that. But you can see how it is coming, how the TensorBoard logs are coming. And then this is the custom loss function. The next part is where I'm defining a custom loss function. I'm naming it as Huber loss. So it is a loss function that is sensitive to outliers in the data compared to like the mean squared MSE loss. So it behaves like MSE for small errors and like the MAE for large errors. It is a robust loss function. So this is how we're using it. This is the implementation, and this is what it is. So for the small error, it is coming as MSC, and then for a large errors, it will be coming as MAE, which is nothing but mean absolute error. So you can see training with custom Huber loss. And then yeah, this is the compilation. I'm adding the layers, everything. These are the results. And this is the analysis that we've done. So it indicates that the model is successfully learning to minimize the error between its predictions and the true values. And then after that, we have the next part is custom activation, initializer, regularizer, and constraint. So in this, I have four different things that I'm doing by custom. Custom activation using leaky relu and custom initializer using my glorot initializer. And then regularization, I'm following the previous thing, whatever I did. I just created a similar regularizer to L1 and I'm using that. And then for custom constraint, I'm using my positive weights. So here in this, it defines the restrictions on the values or the weights during and after training. So you can read all of these values, all of these from my collab. And then we define all of these custom components as such. Let's start with the custom activation, which is nothing but leaky relu. This is the custom initializer. This is for the custom regularizer, and then we have the custom constraint for the weights. So I'm creating a model with that, and as you can see, as you can see with all of these custom values, we got an accuracy of 0.77, which is kind of less. So I mean, depends on the hyperparameters and etc. all of that, whatever customer defined. So maybe by using different parameters to these, we can improve the accuracy instead of this. So that because the combination of this custom components, particularly the L1 regularizer and positive weight constraint, might be limiting the model's capacity or making the optimization more challenging. So that is why the accuracy is reduced. Let's go to the next one where we're using custom metric. So we're defining something called as a Huber metric, and it is inheriting from Keras metrics.mean, and it is used for computing the average of the stream of the values. We are defining the custom metric over here and then doing the same thing, compiling a model based on that. So Huber metric training. So we can see that shows the value of the Homer metric during the 100 epochs of training. It starts at approximately 5.51 and steadily decreases to 5.13. So decreasing value says that the model's predictions are getting closer to the true values over the training process. So yeah, that is why uh, we can use it to reduce the discrepancy. So here I'm just doing the next thing is like implementing our own custom layers. So I have four layers over here. One is the exponential layer, the next is the Midens, add Gaussian noise, then layer normalization. So we have four layers, and then this will be the first layer, and then this is the exponential transformation after the first layer. This is for adding noise for regularization, and then this is the layer normalization. And then after that we have a standard dense as output layer. So layer 1, layer 2, layer 3, layer 4, and these are the layers. and then we have the dense output layer over here. And then after all of this training, you can see that the accuracy is 86%, which is good. So we've done good work over here. And then here I'm just defining my own custom model, as you can see, called regular residual regressor and residual block. And then residual block is for basic residual connection. And then for the regressor, we are inheriting from Keras.model. So this is for the residual block and this is the residual regressor. So based on this, we are creating our own custom model. So you can see the graph for this. So we can say that the decreasing MSE loss indicates that the custom uh, re residual regressor model is successful. It is successfully learning to fit the synthetic regression data. So that is about creating our own custom model using residual regressor and um, residual block. After that, we have the next part where we're using custom optimizer. So I've named a optimizer called my momentum optimizer, and I'm doing this for as the custom thing. And optimizers basically are algorithms that adjust the model's weights during training to minimize the loss function. So we have we're defining this from optimizer, and we have these constructor. This is a constructor. These are the different methods that we have. So this is my custom optimizer, as you can see. And then we have different methods. This is a constructor, this is a build, this is the update step, and then the get config. So on the MNIST dataset, we're doing the same thing, building the model, and then for usually we use Atom optimizer, but here we're using the custom optimizer, as you can see. Let's see the accuracy, and yeah, this is the training. Everything is done, and then yeah, this is all about using a custom optimizer. Let me see. I think I was getting some error. Mm, yes. Oh, so this is where I ran it. As you can see, these I think I was facing some issues, so I just have that code. But yeah, this is how I fixed it, and this is the loss that I have, and then the accuracy that I have. So as you can see, these are the predictions, and then these are the true labels. As you can see, the only thing we got wrong was 5 was predicted as 6, so that is the only wrong thing. That makes sense because our accuracy is around 93%. So yeah, this is all about that custom. Yeah, this is all about the custom optimizer. Let's move on to the custom training loop. So we can basically what we can do is we can use a fit model, and that is used for training the models, right? So we can use a custom training loop that offers greater flexibility and control over the training process. So that is why that is what we're going to achieve in this. So it basically like a custom training loop typically involves manually iterating over the dataset, calculating the gradients, updating the model weights using an optimizer. So it allows us to customize the loss calculation, gradient application, logging, and other aspects of the training procedure. So taking the dataset, I'm going through the code. This is the optimizer that we're using. As always, we're using the Atom optimizer. This is the loss function. So yeah, so this is the training loop function, and then this is where we're doing the custom training loop, as you can see, and then we're evaluating that. So we're starting with the yeah epoch 1, 2, 3, 4. So each epoch we're just keeping the training accuracy with us. So after 4 epochs 0.98, yeah. So I gave 5 epochs, right? So we got the accuracy at 98.66%, which is really good. So the results of the custom training loop are very encouraging. The high training accuracy derived at the end of the 5 epochs that suggests that the model has learned patterns. So this is all about the advanced Keras constructs. So basically we achieved all of this. Whatever we did, whatever I mentioned over here are achieved in one single collab. So yeah, this is all about the part 2. Thank you.